Hello. How are you guys so far? How are you guys feeling about the exam coming up so far on Wednesday?
Scared.
Scared? Oh shoot. Yeah. Are you caught up with the like alkyne reaction stuff yet? Because I know she didn't finish the new material, but I recommend like just looking that reactions up, like finishing the chapter by yourself, so that you have more time to practice those reactions, mechanism, synthesis. And then tomorrow when you guys have lecture, it won't be like all new to you guys. Like it will be like the second or third time you guys are looking at it. Have you guys looked at the remaining of the alkyne chapter yet, or not yet?
I'm kind of waiting until lecture to
To
ask.
learn the alkyne.
Yeah, I learned whatever has been covered about alkynes so far, and the rest is just supposed to be the stuff we learned for alkenes. We just do it twice for the
Mhm.
electrophilic addition.
Right.
So I think it should be pretty self-explanatory, but
Yeah. Alkyne is basically just alkenes, but everything twice, like you said. Like it's just like the alkene reactions, but one more.
yeah. So I don't know. I
It's
feel
really
like there's
short.
too much content to put on one note card because we're literally doing 1.5 midterms.
I know. Wait, 1.5 midterms?
Yeah, because we're doing chapter 13 because Helix was giving
Oh
what
yeah,
it,
yeah.
yeah.
Mhm. Oh well, he looks he has like 3 midterms and he dropped the lowest midterm. Um, but for Levens, I think she does 2 midterms and she doesn't drop the lowest midterm, right? She accounts those two as
Yeah.
the grade. Yeah,
Yeah.
right.
Wait,
Um,
would you be able to go through the NMR
oh
from
yeah, let's do it.
practice midterm?
Oh, the
That
practice midterm. Okay,
yeah.
for sure. Yes. Okay, so the first thing I do for the spectroscopy problem is I calculate the degrees of unsaturation, which is going to be the formula 2c plus 2 minus h minus x plus n all over 2. So in this case, we have 2 times 16 plus 2 minus 26, uh, 2c plus 2 minus h minus x. So there's no halogen here. There's no nitrogen here. So I'm not going to do anything else. I'm going to divide all of that by 2. So that's 32 plus 2. That's 34. 34 minus 26 is 8. 8 over 2 is 4. 4 degrees unsaturation. And then whenever I have at least 4 degrees unsaturation, I assume that we might have a benzene ring, right? But to confirm that, I could check if there is anything between 6 to 8 or 6 to 9, because that's where the benzene hydrogens are at. But there's nothing here, so we do not have a benzene ring, right? The next thing I look out for is the IR, right? So in the IR here, we see that we are going to have um, an sp2 carbon hydrogen bond from the 3100 peak, which means that we have a sp2 carbon that's bonded to hydrogen like that, which is this sp2 carbon to hydrogen bond. 2900, that's the regular sp3 carbon hydrogen peak, so that's almost always there. Um, the 2100 to 2300 peak is the alkyne region on the IR, which is either going to be your, oh, I mean your triple bond region, which is either going to be an alkyne or a nitrile, right? But in the chemical formula, we do not have a nitrogen, so I'm going to cross out the nitrile as an option here. And whenever we have an alkyne, it could either be an internal alkyne or a terminal alkyne, right? But if we have a terminal alkyne, like let's say something like this at the end of the chain, then we would also have a sharp peak at around 3300 or 3400, right? But we don't have a sharp peak at around 33 or 3400. So we do not have an sp carbon hydrogen bond or a terminal alkyne. So this alkyne that we have right here is going to be internal, somewhere in the middle of the molecule, right? Internal alkyne. 1700 is going to show me my carbonyl, carbon double bond oxygen. 1600 is going to show me my alkene, C double bond C, right? Because whenever you have this 3100 peak, the sp2 carbon hydrogen bond, you will always see this peak that goes with it, that pairs up with it. The peak around 1600, the alkene C double bond C peak, right? These numbers I ignore below 1500, which is the fingerprint region. So what I got from the IR is that we have an sp2 carbon hydrogen bond or an alkene, a carbonyl, and an internal alkyne, not terminal alkyne, not a nitrile, right? And that's where my 4 degrees of unsaturation are coming from. 1 from the alkene, 1 from the carbonyl, and 2 from the alkyne, right? That's 1 plus 1 plus 2. That's 4 degrees of unsaturation, which we have right here from the first step. Right. The next step I do is look at the HNMR and get the fragments from that. So let's look at the most de-shielded peaks here, which is between 4 to 6. And between 4 to 6, that's the alkene region, the alkene hydrogens region. Right. So we see HA and HB are going to be the hydrogens directly on the alkene, like that, right? Like any hydrogen on the alkene, like directly on the alkene, is going to be between 4 to 6 on the HNMR, right? We also see HC and HD having J values, but they are between the 2 to 3 region, right? That's not the hydrogens directly on the alkene. The 2 to 3 region is going to be called the alpha region or the allylic position region, right? Where those hydrogens are, let's say, on the alpha carbon of the alkene, 1 carbon away from the alkene, right? Not directly on the alkene, but it's attached to the carbon adjacent to the alkene, 1 away from the alkene, right? So now let's look at the relationship between HA and HB. What are they to each other? Are they going to be cis, trans, or geminal? Right? We see HA and HB, they share a J value of 17, which means that HA and HB are going to be trans to each other. Right? Because I think a J value of like around 16 is trans, which 17 here, since they match HA and HB, are going to be trans to each other. Right? And you don't have to use all of the J values here to get the correct thing, right? Right now, what I have based on the J values here is that the alkene we have is going to be trans, right? I don't know what's attached to here yet. Right? But I do know that HC has to be somewhere here, and there's only one HC, right? And then HD also has to be somewhere here, where there's 2 HDs, because we see 2 HDs right here, right? So if we only have 1 HC, then that means that we are gonna have 2 different R groups coming out like that, right? So I'm just gonna guess here. I'm gonna guess that we have something random there, something random here. I don't know what that is yet. And then I'm gonna put HC right here because we have one HC hydrogen, and then we have 2 HD hydrogens, which are gonna be like that, right? And I don't know what's attached to here yet, but I know that there's 2 HD hydrogens here. Right? And specifically, we see that HA and HC here, they have a J value of around 7. Around 7 is what Levens calls allylic. And what that means is that, let's say we have this alkene right here, and let's say this is HA directly on the alkene. The allylic hydrogen is going to be on the opposite carbon of the alkene where HA is. So it's not on the same carbon where HA is. It has to be on the other end, the other carbon of the alkene, right? The alpha carbon of that carbon, right? Hydrogen right there. That's allylic. Any questions on that position, like the allylic position term, where and HC here are allylic to each other, right? It's not going to be this, where HC is on the alpha carbon, which is on the same carbon as HA, right? That's what I said last time, but what Levens calls this relationship is alkane, which is between 0 to 3, right? That's the relationship between these two hydrogens that I just drew here in the laser, right? But what she calls allylic and what she refers to that as around 7 hertz is going to be this relationship here between HA and HC, where HC is on the alpha carbon that is on the opposite end of the alkene carbon of HA. So that's the allylic one, right? So HA and HC, they are going to be allylic to each other. So the way I drew it here is wrong, right? The way I drew it here is going to be wrong because this right here, HA and HC are alkane to each other. So if it's like this, then they should have a J value of around 3 to 4-ish, right? But HA and HC has a J value of 7, which means that HC has to be right here, the alpha carbon on the opposite end of the alkene, right? And there's only one HC, which is why I drew out one HC right there. And if there's one HC on that alpha carbon, then that means that it's attached to 2 other things that I don't know yet, right? And then we see that HB and HD, they have a sharing J value of 8, which means that they are also allylic to each other, right? So HB and HD are allylic to each other. And there's 2 HDs here, which is why I drew out 2 HDs right there. And I do not know what's attached to that end yet. So this is the alkene I have based on these J values here, right? Okay. And we could also confirm that because HC and HD are on the alpha carbon, which is 1 carbon away from the alkene, which is why they're showing up between the 2 to 3 range on the HNMR, the alpha region. Right. Now let's look at this peak here, where it's between 3 to 4, the electronegative region, right? These 2 hydrogens here are right next to an oxygen, or electronegative atom. And in this case, I'm saying it's an oxygen because our most electronegative atom in the chemical formula here is an oxygen, right? So since we also have a carbonyl, I'm going to assume that we have some kind of ester, right? Because a lot of these practice problems, if we have a carbonyl and there's 2 oxygens, then you could assume it's an ester. That's not always the case though, because it could just be a ketone and then the other oxygen is like an ether or something like that, right? But right now, I'm gonna guess that it's an ester, and if it doesn't work to like fit everything else, all the other information, then I'm gonna switch it up and make it a ketone, the carbonyl, and then the other oxygen and ether. But right now, I'm gonna go with an ester, right? Which is gonna be something like this. These 2 hydrogens here, that is between the 3 to 4 range, is gonna be right here, right next to the oxygen, right? The carbon directly attached to the oxygen, right? And let's highlight that yellow. These 2 hydrogens here are these 2 hydrogens right there. We see that those 2 hydrogens is a triplet, which means that they have 2 neighbors. So I'm gonna draw as 2 neighbors like that, 2 neighbors. Now, I'm gonna say that I just drew out those two hydrogens out randomly. So I'm gonna highlight those 2 hydrogens and make it those 2 hydrogens. That's just a guess right now, right? And it does make sense right now because it's between the 0 to 2 range, which is the boring alkane range, right? Values for allylic and alkane are swapped. What did you say? The values for allylic was it 0 to 3 and alkane is 0 to 3, or yeah? What was the values for this right here? Alkane is around 7 and allylic. Okay, so if alkane is around 7, then this is what she considers alkane. Right, so this is gonna be alkane. Right. And then if it's allylic, then that's gonna be the other one, the one that I said last time, around 0 to 3 allylic is going to be when we have, let's say, HA, and then on the same carbon where HA is, on that alpha carbon or the allylic carbon, that's where, let's say, HC is, right? If HA and HC, let's say they have a J value of 3 hertz, matching J values of 3 hertz, then they are allylic to each other, meaning that this is the relationship between HA and HC, right? Coming off of the same carbon of the alkene, right? HC is on the alpha carbon relative to HA. For alkane, that's the 7 hertz one, where HC is still on the alpha carbon, but not on the same carbon as HA. It's on the opposite end of the alkene, right? So that's still gonna fit in here, HA and HC, but they're not considered allylic. They're considered alkane. Alkane, right? Same as for HD and HB. They're not considered allylic, but they're considered alkane because they have a J value of around 7 here. Alkane. Okay. Okay. Right. So now we see that these two hydrogens here that are pink, they have a quintet, which means that they have 4 neighbors. We already see its 2 neighbors here drawn out for us. So to give it another 2 neighbors, I'm just gonna put in 2 hydrogens right there, which let's highlight that blue, right? I just drew out a set of hydrogens, which is gonna be those 2 hydrogens right there, right? Which is also between the 0 to 2 range, which is at the boring alkane range, not next to an electronegative atom, not next to an alkene, right? So those blue hydrogens there would also have 4 neighbors because it's also a quintet, right? But there's no more like set of peaks that has 2 hydrogens, right? This is 6 hydrogens, this is 9 hydrogens. So these 2 hydrogens right here that are the other neighbors of the blue hydrogens has to be an existing hydrogen that we already used up, right? HA had 1 hydrogen, HB had 1 hydrogen, HC had 1 hydrogen, HD had 2 hydrogens, right? So because HD had 2 hydrogens, I'm gonna say that the other 2 neighbors of the blue hydrogens is HD. So that's why we're gonna connect the alkene from, right? That's why we're making that connection between those fragments right here, right? So if I'm making that connection, like where I'm saying these 2 hydrogens right next to the blue hydrogens are HD, because I can't say that it's another random set of 2 hydrogens because we don't have any other peaks that represent 2 hydrogens. It's just HD. That's where I'm gonna connect the fragments, and we know what's attached to HD, which is the trans alkene, which this is gonna be HA, this is gonna be HB, and then right next to that is gonna be HC, and I don't know what's attached to here yet. Right. Okay. Let's cross out the peaks that we already used up. HA, HB, this one, we used up that one, we used up that one, we used up that one, that one. Now, we haven't looked at these 2 peaks yet. When you see like this really long singlet peak with 9 hydrogens right here, in 118A, you guys learned that that's a common peak for a common group, which is just tert-butyl, right? Because these 9 hydrogens here are chemically equivalent. They have the same chemical environment with 0 neighbors. 0 neighbors, singlet. Right, so we have a tert-butyl somewhere. When you see 6 hydrogens right here with a doublet, then that's a sign of another common group, which is an isopropyl group, right? Where the 6 hydrogens that have the same chemical environment are going to be these 6 hydrogens right here, and its one neighbor is going to be this one neighbor right here, right? Which is why it's going to show up as a doublet right here, right? And then we could say that 1 hydrogen right here, since I don't see any other one hydrogen peak, except for HC. I'm gonna assume that that one hydrogen is HC right there, and this matches up perfectly because this isopropyl group right here that we see can be these isopropyl groups right here, right? We can make that the isopropyl group, where the 6 hydrogens are going to be these 6 hydrogens right here, 1, 2, 3, 4, 5, 6, with one neighbor HC, right? And that goes with these 6 hydrogens right here. Okay, so we cross that one out. So the fragments that we are missing are going to be that tert-butyl, and we said that we had an internal alkyne. We have not used that internal alkyne yet, right? We have one more spot to fit in that internal alkyne and tert-butyl, right? But before we do that, we know that we have 16 carbons in the chemical formula. Let's see how many carbons we used up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 carbons. So that means we can use 6 more carbons, right? So I could either put a tert-butyl there, which ends the chain. I can't add anything else, right? And that's going to be, let's say, 11, 12, 13, 14. That's short. And we can't add the internal alkyne as well. So we got to add in the internal alkyne and then the tert-butyl, right? And that ends the chain right there. Now, when we count the carbons, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 carbons. So that matches with the formula. Let's see if we have 26 hydrogens, right? 3, 6, 9, 11, 13, 15, 17, 18, 19, 20, 23, 26. 26 hydrogens and 2 oxygens right here, right? So that verifies the chemical formula. Let's verify the degrees of unsaturation. 1 from the alkene, 1 from the carbonyl, and 2 from the alkyne. 1 plus 1 plus 1, 1 plus 1 plus 2, that's 4. 4 degrees of unsaturation, which is what we got, right? Now let's verify with the IR. We have an alkene, we have a carbonyl, and we have an internal alkyne. Internal alkyne, not terminal alkyne, right? The J values also make sense because in the J values we saw that we had a trans alkene, and then with all the alkane hydrogens, like HD is alkane to HB, and HA is alkane to HC, right? Yeah. You could also say that HD is allylic to HA, which makes sense, but it's kind of harder to see in this case because they share J value of 1, right? But there's a lot of ones here, right? HA is alkane to HD, and HC is alkane to HB. So they also share J value of 1. But these ones here, like since there's a lot of them, like that's not as important, right? To figure out first. The most important thing here is like the trans alkene, the 17 hertz here. And then there is a difference between 7 and 8. So that difference helps us determine what's alkane to what, right? The 7s here lets us know that HA and HC are alkane to each other, and the 8s here lets us know that the HB and HD are alkane to each other. The 1H's here, they're not that useful because there's a lot of them. A lot of them are matching, right? But that's why you don't have to use all those J values. Use the most important ones to figure out the most important relationships here, right? Okay. Into oxygens, that's good. And the HNMR, like things make sense as well, like the number of neighbors, integration, where they are, like de-shielded, what region they're at. Yeah. And then let's see. Yeah. So on the key, you put, wait, 1, 2, 3, 4, 1, 2, 3, 4. That's their internal time. And then tributyl. Let's get rid of these hydrogens. Yeah, 1, 2, 3, 4 CH2s. So this structure is the same as this structure. It's just flipped. Just flipped, but it's the same structure. Okay. Transalkene. Okay, but you'll get majority of the points if you get like the transalkene, you get the carbonyl, you get the tert-butyl common group, and you get the isopropyl group, right? If you put those fragments clearly on your exam and you try to piece it together and you get the correct degrees of unsaturation, then that's where you get the majority of the points, right? The minority of the points is connecting them all together into the specific correct structure. Right? And that's if you have like time at the end. But I recommend like getting all the correct pieces, correct fragments together, and then at the end, try your best to piece them together into the correct structure. Have you guys practiced the NMR worksheet that she posted on Canvas? And were you guys able to get some without looking at the key with this thought process? And notice how I didn't use the CNMR at all. Like you could use it to confirm functional groups, but I never use it to get the correct structure. It could be useful in 118C at the beginning, like the carboxylic acid chapter, but for now, we don't need the CNMR that much. Have you guys been able to do these NMR problems on practice?
Uh, I have, but it was really hard. So I didn't get like all of them right or like full points, I'd say.
Right, but you got the correct functional groups from the HNMR, like the common groups as well, and the alkene.
Yeah.
That's good.
Yeah, but I just was never able to like have the actual correct structure.
Oh, like piecing it together.
Yeah.
Right,
That
that's
part is always the hardest for me.
right, and that's like where the HNMR comes in with the number of neighbors, right? That's the specific part of it. That's the hard one, yeah. Right. Dang. But were you able to analyze like why the correct answer is the way that it is based on all the other information you get? Like you look at the right answer on the worksheet, the answer key, and then you analyze each hydrogen peak on HNMR. Like, oh, that has that many neighbors, that has that many neighbors, and then like make sense of the correct answer choice for the next practice problem. Like were you able to like analyze the correct structure?
Oh yeah, it was just like a lot of like things that I didn't consider. I just
Yeah.
need more practice.
Right. The more practice you do, the more things that patterns that you recognize and things to consider for the next one. Right. Anything else that you guys want to go over today?
Can we just do more like spec? Like, I think that's the only thing I have difficulty with. Like, everything else is okay.
Yeah.
I just need
And
practice with
I'll do a spec problem that I haven't looked at yet too. I haven't looked at the key yet. So then you guys can see my raw thought process on it and a lot of trial and error on this, right? Where I will get it wrong the first few trials, but I will try something new until I get it right. And you guys are gonna see that process as well. Okay, send this. Yeah, let's also go over some synthesis reactions after we go over. Actually, yeah, let's do that one more spectroscopy problem, and then after that, let's focus on synthesis problems, right, for the rest of the session. Yeah, let's do this one. Which number do you guys want to try here? Let's do one more, and the rest of the session synthesis problems. Wait, which compound here? Okay, let's just do a random one. Let's do compound. Okay, I don't know what this is. Wait, I haven't looked at this yet. Okay, so 2 times 9 plus 2 minus 14 all over 2. There's no halogen, no nitrogen. That's 18. plus 2, that's 20. 20 minus 14 is 6. Right? 6 divided by 2 is 3. 3 DOU. Okay, let's look at the IR now. Sharp peak at 3300. That's the sp carbon hydrogen peak, which is our terminal alkyne. Terminal alkyne functional group. And if we have a terminal alkyne, then we are going to expect a peak at 2100 to 2300, which is there. So that confirms that we have an alkyne. That's 2 of our DOU already. We have 1 more to account for, right? 3100, that's the sp2 carbon hydrogen peak, which is the hydrogen on an alkene like that. And if we have that peak, then we are going to have a peak at around 1600, our alkene peak. So we have an alkene as well. So we have a terminal alkyne. In the last example, we had an internal alkyne. In this example, we are going to have a terminal alkyne at the end of the molecule and some kind of alkene. Right. This one, ignore fingerprint region. This one, ignore regular sp3 carbon hydrogen bond. So in the IR, I got that in our molecule, we are going to have a terminal alkyne, an alkyne somewhere in the end of the molecule, and some kind of alkene, right? And that's 3 of our DOUs right there. 2 from the alkyne, 1 from the alkene. Okay. Now let's look at the HNMR. Let's look at the alkene range, 46, HA and HB. We also see HC and HD on the alpha range, but let's look at the J values now. Right, draw some kind of random alkene for the J values. And now this is a matching game. Let's see what numbers match. There's no there's no trans numbers. There's no. Let's see, cis is like around 10, 8. It's weird. This is gonna be weird. What is this? This is gonna be some germinal alkene. Germinal alkene, I guess. Let's see. 7. 1, 1, 2, 2. Okay, this is so weird. Let's see what's going on here. There's 7 here, but there's no other 7. 7, that's not 7. 7, 7, 7, 7. Where's 7? Okay, nothing matches with 7, nothing matches with 6. So that's not gonna be anything there. There's 2 here. There's also 2 here and 2 here. And there's also another 2 there. Okay, I'm gonna guess that this is a geminal alkene, somewhere at the end of the chain, like this. I don't know for sure yet, right? But that's what I'm going with right now. That's so weird. It can't be cis, right? Huh. I'll go back to that peak. Okay, what's our electronegative atom? 1 oxygen. Okay, so that 1 oxygen right there is not going to be a carbonyl, not a carbon of 1 oxygen, because we do not see a sharp peak at around 1700. Right, so I'm going to say that's going to be either an ether, ROR, or an alcohol. Right, but I know that we don't have an alcohol as well, because there's no broad peak on the HNMR, and there's no broad peak at 3300 or 3400. Right, we have a sharp peak at 3300, which represents the terminal alkyne peak, right? Not a broad peak. A broad peak at 3300 shows an alcohol, but no alcohol here. So we have an ether in this structure, okay? And then I see that this is the electronegative region. So I'm gonna put the oxygen right here. One end of it has the CH3, the other end of it has the 2 hydrogens, right? The 2 hydrogens here are going to be these 2 hydrogens. The 3 hydrogens here, H, 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 are going to be these 3 hydrogens right here with 0 neighbors. But it is de-shielded right next to the oxygen because it's at the 3 to 4 range. The 2 hydrogens that are highlighted yellow has 2 neighbors because it's a triplet. So I'm going to draw out its 2 neighbors out like this, H and H, right? And I'm going to say that those 2 hydrogens right there are going to be these 2 hydrogens right here. Wait, that's a guess. Which has 1, 2, 3, 4. It has 3 neighbors. Right? We already see 2 of it right there. We have to give it 1 more neighbor, right? So 1 neighbor right here. And I know that these 2 hydrogens right here are not going to be next to an alkene right? This is not going to be an alkene because this carbon here is not on the alpha carbon, right? It's, well, it is, right? Because 2 to 3 range, we said earlier, is the alpha region. So that means that this carbon right here that's holding the pink hydrogens is on the alpha carbon. So because it's on the alpha carbon, that's why I'm going to put my alkene right there, right? Because if I put the alkene right there, then that makes this the alpha carbon, which makes that between 2 to 3, right? And then its one other neighbor here is going to be, let's see, what has one hydrogen? What is this? This is, okay. Okay, let's just do some random guesses now. Okay, let's see what's going on. Alpha region. Terminal kind. Two hydrogens, two hydrogens. Okay, so I'm not gonna do that. Yes. Okay, let me just try this here. See if it makes sense. What kind of alkene is this though? Is it trans? It's not trans. It's not cis. There's no cis. Terminal alkyne. So the alkyne, I'm just gonna put it at this end right here. I don't know what it's connected to yet, but let's see how many carbons we used up. 1, 2, 3, 1, 2. That's 5. 4 more carbons. 2 of them has to be the alkene. So let's just make that random alkene like this. And then we have 1 hydrogen with 2 neighbors. So we're going to put that in somehow. 1 hydrogen with 2 neighbors. 1 hydrogen with 2 neighbors. Let's see here. 2 neighbors. Okay, let's do it like this. Boom. Boom. And boom. Okay, that was just a random guess. Wait, no. Wait, this 1 hydrogen here will have 3 neighbors, so that doesn't work out. Let's see, what can we do? And that's 1, 2, 3, 4, 5, 6, 7, 8. That's 8 carbons. That's 1 short. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's try something else. Now this is where I start guessing and hope for the best. I just start praying and guessing here. Let's see here. But I do know that we have a terminal alkyne and we have some kind of alkene. And the alkene here is kind of weird because the J values are really weird. Here, let's see. 2 hydrogens are pink with 3 neighbors. Okay, let's say it's like that, right? And I'm going to highlight that 1 hydrogen right there, that 1 hydrogen right there, which has 2 neighbors. And its 2 neighbors here are going to be this right here. So this can't have anything. This can't have anything. What's going on here? But this has to be on the alpha carbon. So let's make that actually the alkene. Hydrogen. Go down here. Do that. That. Let's see. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That's too short. 2 carbon short. Yeah, how about this one? 1, 2, 3, 4, 5, 6, 7. What else do we have? How about this one? 1, 2, 3, 4, 5, 6, 7, 8. That's 1 short. Just adds 1 random carbon somewhere. but that we don't have. Let's see, plane of symmetry here? No. But that's gonna make it a trans alkene, and we don't have a trans alkene, so let's try cis. Let's make it a cis alkene. That's one H1H. That's 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 carbons, 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens, 1 oxygen. But this does not look so good. Okay, the 2 hydrogens right here are could be these. Okay, so what I highlighted is going to be not those 2 hydrogens, right? These 2 hydrogens right here are going to be and let's make this cis alkene, not trans alkene, right? Because we don't have any trans J values. And then that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Terminal alkyne. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. The pink hydrogens here are going to be I see the D hydrogens. There's 2 D hydrogens. HD, HD. Let's put the alkene right here then, actually. Right, because I see HD has a triplet, but there's also a doublet of the triplet. If you see this doublet right here and the triplet, then that means that those hydrogens here is right next to a terminal alkyne, right? That one hydrogen of the alkyne right there is affecting the peak of this HD right here, right? It looks like a triplet, but this is a doublet of a triplet. So when you see a doublet of a triplet, then that means that those 2 hydrogens are alpha to a terminal alkyne. So the HD here is right next to a terminal alkyne, and because it also has J values, it's next to this alkene, this really weird alkene we have here, right? So let's do this like this, right? And then make it cis. And these are the HDs right here. HD, HD, terminal alkyne, next to terminal alkyne. Right, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's the pink HD right here. HA, HB somewhere here, right? HH, and then HC. It's also a doublet, but triplet. It's right here. HC. HC. Okay. But we also have 2 hydrogens that has 3 neighbors, but this 2 hydrogens here has 1, 2, 3, 4, 4 neighbors. That's way too many neighbors. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's way too many neighbors. So what I'm going to do is I'm going to move the alkene 1 over, and then I'm just going to say that that's my final answer because I don't have that much time in the exam, and then we'll check with what it is afterwards, right? Okay, put the alkene right here instead, right? And I do that. Let's make sure this is right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I'm just going to say that that's my final answer because I don't have that much time on the exam, and let's check it with the actual key and see if I could get majority of the points or not. And make this a cis alkene, not trans alkene. CH2, O, and methyl group. Okay, make sure this is 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 1 oxygen. We have 4 DOU, 1 from the double bond, 1 from the triple bond. And this triple bond here is a terminal alkyne, which we got from the IR. and we have an ether here, which is good. And the alkene here was really weird. The J values kind of confused me, but let's check the key for K. Let's see. And then this we want to synthesis balance. C, K, A, B, C, D, E, F, G, H, I, J, K. Here. Okay, so it was I knew it. Gemino alkene, something like this thing, but didn't try that. Not a cis alkene, right? Because cis alkene, these two hydrogens here would have a J value of around 10. I didn't see any 10 here. So I was kind of confused, but it's geminal. Geminal meaning that these two hydrogens here are on the same carbon, right? And then this side here has CH2, and then the terminal alkyne, terminal alkyne. And the other side has CH2, ether, right? So I'm gonna circle the fragments that I'll get the credit for. This ether here that has a methyl group, which is that ether with the methyl group right there. This terminal alkyne, which is this terminal alkyne right here, right? And then I did include the alkene, which is this alkene right here, but I did not get the correct alkene. I got the cis alkene, but this is a geminal alkene, right? And a geminal alkene, the geminal hydrogens are gonna be like J value of like around 0 to 2, right? That's why it was so weird. So if you see on your J values, there's no 10 matching hydrogens. There's no around 16 matching hydrogens, right? There's no cis or trans alkene, right? If you just see low numbers like 0, 1, 2, or 3, then assume that your alkene here is geminal, which in this case, it was geminal, right? There's no cis because there's no matching J values of around 10 or 11 or 8, right? There's no trans alkene because there's no J values of 16, 17, or 18, right? It's all low numbers. So you assume geminal hydrogens, meaning that the two hydrogens here are on the same carbon, right? Coming off of the same carbon, right? Okay, let's see. For DOU, check. Yeah, so I didn't get the correct structure here too. The alkene I got was off, right? But I got the fragments, which is terminal alkyne and the methyl ether here. Okay. Okay. Ready for synthesis problems? Okay, I'm gonna involve alkene and alkyne reactions as well in the synthesis. Let's see. Okay. Let's see. You haven't learned about hydration or hydrogen oxidation of alkynes yet, so I'm not going to include those reactions. But I think you will learn about those reactions tomorrow in lecture. Right. So let's just use some kind of other reaction. This reaction you have learned. Let's do that. Go here. That. And let's do this. Wait. Get rid of this. Right, and then put that there. Yeah, that. Okay. Do this one here. Yeah, let's do this one. From this alkene to this dihalogenated alkane. Okay, let's try that synthesis problem. while you guys work on that, I'm gonna come up with another one so then we could work on that afterwards. What am I trying? Mhm. Okay, yeah, that's good. Okay. Did anybody try the first synthesis film here? And so what did you guys try? Think about it backwards, forwards, and try meeting in the middle. What's the similarities and differences between the reactant and product molecule? What functional group you see on the product? What reactions you could think of that created that functional group to go backwards? Like for these synthesis forms, you have to like really know the reactions, and that's why you do like the predicted products, label each reaction so that you know like what reactions give you what. So then those will be the tools that can serve you on these synthesis forms, right? So what reaction do you guys think is going to happen in this first synthesis here if we have this dihalogenated alkane, two halogens on the same carbon, right? What reaction do you guys know that can give you that product? That's thinking backwards, retrosynthesis. You don't have to do that, but that's how I recommend starting, like going backwards. You could have went forward as well, right? But let's think about it backwards here. Okay, so this is one of the newer reactions. It's one of the alkyne reactions, right? Where let's say that because it's only on one carbon, this came from a terminal alkyne right here, right? And then to put the two bromines there on that more sub position, which is this position right here, the Markovnikov position, we put HBr in excess, right? Which is gonna do like hydrohalogenation of alkyne, which is basically hydrohalogenation of alkene, but 2 times, right? Which is why we see 2 bromines on the Markovnikov position, right? Now, do you guys remember how we could form terminal alkynes? Like what intermediate could have came before this terminal alkyne right here? Okay. Think about how we formed double bonds, right? And we're going to do that 2 times. So it was E2 reaction 2 times. So that means that this structure here could have came from this halogen with this haloalkane right here with 2 halogens that are adjacent to each other, right? But if we want to make a terminal alkyne, this is the important thing right here. Make sure if you put a strong base to the E2 2 times, you put 3 equivalents of it, right? That's important. 3 equivalents of it. And then second step, some kind of proton source like water, right? To form your terminal alkyne. It would do E2 2 times for the first 2 equivalents. And then for the last equivalent, it's going to deprotonate the terminal alkyne to give it a negative charge. That negative charge gets protonated by the water, right? Now, if we go backwards here and think about how we could get these 2 bromines that are adjacent to each other, like vicinal to each other, then we could say that that came from an alkene, right? Where these 2 carbons here holding the halogen are the carbons of the alkene, which the reagents we could use for that is Br2 CCl4. And it has to be CCl4. It cannot be water or alcohol, because if we use the water or alcohol, right, then this would be OH or OR. But we want bromine and bromine, so we use CCl4. Right? Now we gotta think about how we can create this less stable alkene from this more stable alkene right here. We saw that this less stable alkene right here can be made by a Hofmann E2 reaction using some bulky base like terbutoxide or LDA, right? But we needed a good leaving group at this carbon here, because that's the carbon where they share, like the alkenes, they're connected to. So we're gonna put a bromine right there, right? And then to put a bromine at the anti-mark position and then hydrogen on the mark position, we gotta use not only HBr, because HBr would put the bromine on the more sub position. We gotta put something else to it. And then think about a lion, right? Think about what sound a lion makes, roar, right? So we're gonna put roar right there, ROOR, to make this an anti-mark addition of Br, and on the alkene, right? We want the Br on the left sub side, so we're gonna put HBr and roar, which is an anti-Markovnikov reaction, right? So this synthesis was 1, 2, 3, 4, 5 steps, right? The first one was radical hydrobromination. The second one was E2 Hofmann. The third one was halogenation and CCl4 solvent. The fourth one was terminal alkyne formation or synthesis. And then the last one was hydrohalogenation of alkyne.
Brian, I have
Yeah.
a question.
Uh-huh.
We use CCl or CCl4, not H2O, because the H2O would compete with bromine, right?
Uh-huh.
In terms of going to the electronegative part, if that makes sense.
Right. It would compete with the bromine because the intermediate for that reaction is this bromonium ion right here, where we have Br minus here. And if we only have Br minus, where CCl4 is a non-nucleophilic solvent, it won't interfere. That Br minus is the only one that would attack the carbon and kick out the bromine to give us what we want here. But if we used water, the water would overpower or overwhelm the bromine minus because that's 1,000,000 times more water than the bromine, right? There's an excess amount of water because that's the solvent, which would overpower the Br minus. So the water would attack instead of the Br minus, giving like this intermediate and then later on deprotonated to become alcohol product instead, right? But we don't want OH here, right? Because we want two good leaving groups to make this alkyne right there. That's right, that's right. But on your synthesis, if you see this as your final answer, where OH or OR is on the more sub side and then BR is on the less sub side, then you want to use water, and that's going to be your final reaction, right? Where the water would make this OH here on the more sub side, more carbon on the top side, right? So depending on what your product is, that's going to determine what reactions you use, right? And what kind of solvent. Okay. Now let's look at the next one here. What reaction do you guys know that makes a vicinal syndiol? What reaction do you guys know that makes two alcohols that are adjacent to each other that are on the same side, that attach on the same side, syn addition? And this is one of the alkene reactions, not alkyne. Right, so let's say this came from an alkene, where the alkene is between those two carbons right there holding the alcohol. Alkene, there. What reaction converted that alkene into this vicinal syndiol here?
Can I guess?
Yeah, you can guess. It's okay if you get it wrong because like we're
Okay.
gonna
Is it the one with the? Oh wait. I'm sorry if I'm wrong, but is it the one with
That's
the
okay.
OSO4?
Yeah, it's
Or
right. OSO4, osmium tetroxide, osmolation. Nice. Right. Osmolation. OSO4 makes the vicinal syndiol from an alkene. OSO4 and second step of, I forgot what it was, NaHSO3, something like that. Right. This right here, it sounds very similar to ozonolysis, but it's not ozonolysis, right? Ozonolysis does something else different entirely, right? But osmolation, the OSO4 one, creates two alcohols, one for each side of the carbon, alkene, on the same side, syn addition. Yeah. Right. Now we're gonna figure out how to make this alkene from this alcohol here. Right. What reaction do you guys know that makes alkenes from alcohols? Right. There's two reactions that you guys learned that makes alkenes. One of it is E2, the other one is dehydration. So which one would this be? Would this be an E2 reaction or would this be a dehydration reaction based on this reactant here? Yeah, dehydration with H2SO4 and heat. Right, H2SO4 and heat. That's gonna go make the. Oh wait, it's actually gonna go there all the way from here all the way to here directly with H2SO4 and heat. Do you guys want me to go over that mechanism as well, or do you guys get like how we got from here to here directly with H2SO4 and heat? Right. Because the first step is to like protonate this OH to become OH2 plus leaving group, and then when it leaves, it forms a carbocation at that carbon, and then we do a hydride shift to make that carbocation into its more stable position here, and then we do an E1 reaction where the conjugate base H2SO4 minus comes back to grab that hydrogen, make a double bond right there to create this alkene right here. Right. When I first made this problem, I wanted it to be more steps, but I just realized that you could go here to here in one step with H2SO4 and heat. Yeah. Any questions on how we got there? I could show you the mechanism like more clearly as well. Okay. Okay, let's move on to the next one here. So in the reactant here, we have a haloalkane. In the product here, we have this structure where we see an OR vicinal to an OH. OR adjacent to an OH. Right? And they're also anti to each other. So what reaction do you guys think happened in the last step of the synthesis here? right? If you see an OR next to an OH, vicinal to an OH.
Epoxide?
Yeah, epoxide opening, right? Where the epoxide came from the carbons between those two groups right there. Which oxygen was the epoxide oxygen? The OR oxygen or the OH oxygen? When we open it up, which oxygen is the epoxide oxygen? Yeah, the alcohol oxygen is the epoxide oxygen. And when we do this reaction here, and we open up the epoxide, the OH maintains its stereochemistry. The epoxide oxygen maintains its stereochemistry. So in the product, if you see the OH is a wedge, the epoxide has to be a wedge, right? Oxygen right there. This ethyl is still right there. And we see that the OR opened up the epoxide on the left subside. It attacked the epoxide on the left subside. So are we opening this up in acidic conditions or basic conditions? Yeah, this is like 118A, like the end of 118A. But I think she might include this on the synthesis as well, because I did see that on the synthesis worksheet, like epoxide stuff. Right. So would the OR attack the epoxide in acidic or basic conditions if we want to attack the less subside, the less substituted side? Okay. So if we want to attack the less substituted side, we want to do it in basic conditions. And in basic conditions, everything is going to be either negatively charged or positively charged, right? So what we're going to use is the first step, NaOCH2 CH3, and then the solvent, CH3 CH2OH. And then second step, some acid workup, like water or H3O plus, right? Don't put those two steps together, because if you put those two steps together, they are going to react with each other, right? The ethoxide here is just going to get protonated. You have to separate them into steps. First step, second step, right? Where the first step, the ethoxide here attacks the left subside, kicks that up, O minus gets protonated by H3O plus later. Okay, so now, how can we create this epoxide here? Like, what reaction do you guys know that can create that epoxide? What 5-letter reagent do you guys know that makes epoxides from, let's say, like this came from an alkene, right? The two carbons that make up the epoxide, let's say those two carbons came from an alkene. What 5-letter reagent do you guys know that makes an epoxide? Right. MCPBA, right? MCPBA, peroxy acid, right? Creates that epoxide. Now we've got to figure out a way to make this alkene right here from this haloalkane. Right. So this is a primary hindered substrate. So it doesn't matter what kind of base we use, because there's only one alpha hydrogen we could deprotonate. If we could use a small bulky base to do E2, let's use NaOH water to form that alkene right there. And now we want to convert this less stable alkene to this more stable alkene. So what we could do is that we see that those two alkenes share that pink carbon right there. So I want to put a good leaving group there, like bromine. So I'm just going to put HBr, right? Just HBr, because I want it to be on the Mark position, Markov-Makov position. And then I could do another E2, NaOH and water, to put the alkene at the more stable position, right? Because these two alpha hydrogens right here are symmetrical, right? They're going to give the same alkene. So we just did another E2 reaction to grab that H, make the alkene there, kick out the bromine to form that alkene, and then MCPBA, and then open up that epoxide in basic conditions. Right. I didn't use roar in this case like I did in the last one, because if I did roar, it's going to go backwards. It's going to put the bromine on the less subcarbon. I wanted the bromine on the more sub position, because I wanted to make the more stable alkene here, right? Which is why we're going to deprotonate that hydrogen, which is symmetrical to this hydrogen, so it didn't really matter. It's going to give you the same products, right? Because they're symmetrical. What else here? Let's see. Yeah. There is like a way to go from the less stable alkene to the more stable alkene, but I don't think Levens went over that in her class. And that is isomerization, where she puts like where you could put acid and heat to convert a less stable alkene to a more stable alkene, where it's still connected by one carbon. And that reaction here is called isomerization, right? I don't think Levens went over that, so don't worry about that. But if she did, then this would be the faster way to make the more stable alkene. Right. Okay. Any questions on these three synthesis problems that I gave you guys? And when you guys practice spectroscopy, make sure to analyze like what you did wrong, what's the difference between your answer and the key, and then avoid that mistake in the next practice problem, right? The mistake I made here was the alkene, right? The alkene, I couldn't figure it out because there was no J value that had a matching value of around 10 or 16. So we had no cis alkene, we had no trans alkene, right? All the J values here have like 2, 2, 3, 3, which that's around the geminal alkene range, right? Geminal meaning that the two hydrogens here are coming off of the same carbon. Right? Make sure to analyze like each practice problem you do. Okay. Yeah. Good luck on the exam on Wednesday. And hopefully you guys don't learn too many things tomorrow for the new material on the exam. But it's like the alkyne chapter is pretty short. It's very similar to the alkene chapter. Yeah. No problem, guys. Good luck. Bye.